Ladies and gentlemen, next we have James Coomer from DataDirect Networks. His bio reads James Coomer, comma, DataDirect Networks Incorporated. Awesome. Only one other thing.
That's fine.
You guys have heard me say this before. I'm going to say it again. I'm leaning into the mic that's not live. Do you guys know what I'm going to say? Well, yeah, but I mean, the real take-home here is we can't do this conference without vendor sponsorship. Now, why am I making a deal about this? You know, when you fill out your survey, which you should do because that will give you an opportunity potentially to you know, win a stuff, I don't know, Kindle Fire, some other product that, you know, people really want. I'm sorry? A GoPro. We get survey responses from people who complain about, you know, too many vendor talks. I'm just telling you, you know, this is an exchange for cash that we receive, which permits this conference to take place. So I'm just letting you know, so when you fill out the survey, you know, if you're complaining about the vendor talks, make sure the ones that you're complaining about aren't the ones that are attached to dollar signs. I would really like to thank DDN for having sponsored this conference and for having been a founding member of OpenSFS. James Coomer from DDN, let's hear it for him.
That did sound a bit like a prologue, as if I was going to give a really boring talk. I've tried to add a few technical details in here to spare you from the pure marketing stuff.
Thank you.
I'm going to go for this arrow. So most of you probably know that we ship Lustre as Exascaler. This is a framework that includes many components. The core components, of course, come from Intel. It's based on IEL. But then ourselves, on our own, and ourselves in collaboration with Intel, develop a number of separate modules that are designed to enhance the functionality or enhance the performance of Lustre on DDN hardware. For this talk, I'm just concentrating on a few modules that really try to help us take advantage better of non-volatile memory, or today, SSDs. So we do have a new system. This is a Lustre appliance. It's the third in the sort of a 5-year generation of SFA systems. The ES14K is the system on the top there, the red system. It's 4U high, and it's got a few features which differentiate it from the previous generations, the SFA 12K and the 10K before that. So it does support standard nearline SAS drives. You can see one enclosure below the controller, but it takes up to 20 of those enclosures, and each enclosure has 84 drives. So in total, with that single controller pair inside the red system, we can have up to 1,680 drives attached to that. But differentiating it from the previous generations then inside this box is a little bit different. So today we have Haswell, and soon there'll be Broadwell systems with the same architecture. And the way we connect the CPU sockets to the disks and the I/O interfaces is via a PCI fabric. So we have quite a beefy PCI fabric inside this system. And that allows us to get maximum performance out of the back-end SAS and also from those SSDs you see in the top of the controller. And this is the other new feature. We've integrated 72 2.5-inch SSD slots into the controller itself. Those are accessible by both controllers, of course. 48 of those SSDs are NVMe, so the fast ones. So there's 72 in total for SAS, and 48 of those can be used by NVMe systems. A little bit more detail for those who aren't that familiar with our embedded system. If you look at the picture on the left here, that's a kind of high-level diagram of the architecture. So you can see there's two controllers, one in the foreground, one in the background. And each controller's got two sockets, CPU 0 and CPU 1. And then we divide the resources of the cores on that system amongst two things. One is, obviously, we need to have Lustre object storage servers. So we have OSSs running on virtual machines inside the controller. And those OSSs communicate with a sophisticated RAID engine called SFAOS. So it's a real-time, about 1 million lines of code developed over 5 years. And the VMs communicate with SFAOS via a block driver. So basically, that's a very fast driver explicitly designed to help VMs communicate in this environment where it's sharing the same shared memory with the RAID engine. So right now, we're on Haswell over here. But then in a few months' time, we'll be just upgrading that CPU to Broadwell. And at that point, you can probably notice we've increased the share of the CPU cores which we can allocate to those object storage servers. So we will see another performance improvement in a few months' time. But this talk is actually about how we use SSD caches within Lustre. And the problem is well known, so I won't spend a long time explaining it. But of course, if we look at the performance in terms of IOPS per gigabyte or the performance in terms of throughput per gigabyte, then SSDs win by a long way, particularly when it comes to IOPS. So in this graph, for a petabyte of data, we're seeing 7 orders of magnitude higher levels of IOPS from an SSD. But they're still pricey. We still need to watch the budgets, and so we need to get the most out of these SSDs. We can do that in 2 ways, which I'll explain during the talk. One is we can optimize the data for the SSDs, and the other is we can optimize the SSDs for the data. Sounds like gobbledygook, but it'll become more sensible. So here's my Venn diagram of all data in your Scratch file system. And some of that data resides on an SSD at any one time, and then some of that data benefits from residing on the SSD. Unfortunately, typically, not all the data that benefits from the SSD is sitting on the SSD. Over time, then of course, economics drives the evolution of larger SSD drives, and we get more data residing on SSDs. That's fine. But we also need to push to increase the amount of data, so the subset of your whole data that really benefits from being placed, so written to or read from an SSD. So let me explain a little bit. Today, it's fairly straightforward, and I'll talk about 2 examples to use SSDs as a read cache. And therefore, we can serve half the IOs, more or less. But we could also use SSDs for a write cache. We can also use SSDs and optimize them better for random IO. We can also optimize them better for shared file IO. And that's what we're trying to do, expand the subset of data which is really benefited by SSDs. And then also, we need to be more intelligent about our data placement. We need to make sure out of all our data, then the biggest possible subset of data that benefits from SSDs are actually placed onto those SSDs. And that requires a bit of intelligence in our data management. So I'm going to use the next 7 minutes or whatever I've got to explain all of that. So we've done some tests. I'll show you some numbers. We can do 4 things here. In fact, there's more options. But in this case, we've taken a system, and we've run SSDs everywhere, a Lustre file system on SSDs. Then 2 and 3 there, where we take 2 simple or relatively simple cache methods, explicitly read cache methods, SFX and the L2 read cache. And I'll talk about the results on there. So in these cases, you buy a relatively small number of SSDs to accelerate the I/O from a large Lustre file system, which is mainly composed of nearline SAS. Then number 4 is a rather more radical, sophisticated approach using infinite memory engine. So DDN's newly GA'd product. It's a software based on a distributed cache. And hopefully, I'll squeeze in a couple of slides on that at the end. So straight into number 1, all SSD Lustre. So here are some results. We've got 10 ES14Ks in a rack with 2 U to spare. And we measure the performance of that using IOR from many, many clients. And we see that from each ES14K, we achieve something over 35 gigabytes a second for this embedded system, which means for 10, we're getting 350 gigabytes a second for both reads and for writes. So and in a single rack, we also get just under 4 million IOPS for 4K random reads. So step 1, a single rack of ES14Ks, we can achieve over 350 gigabytes per second. So about the cache options. So if you haven't got enough money to spend your all of your money on SSDs for the whole file system, then at least you can spend a relatively modest portion on some SSDs to accelerate those IOs that benefit from it. We've got 2 methods here. This one is demonstrating how SFX works. So here the picture you see in OSS, it's connected to a controller. In the controller is some memory, some hard drives. We've added some SFX SSDs. So for large reads, these will be accessed directly from the hard drive tier. For small reads, initially, they'll come from hard drives as well. But SFAOS will intelligently take those small IOs, and those data accessed by small reads will trickle down into this SFX tier, so that subsequent rereads will all be served with very high IOPS from a small number of SSDs. We can also add a bit more intelligence. So rather than relying upon SFAOS to do this, well, it's the least recently used an LRU caching algorithm, we can use Intel's differentiated storage services to pull that data in explicitly. And here's what we get. Similar to what we saw before, for 4K random reads, what you're seeing here is a 10-fold increase by adding just 4 SSDs. And we're comparing 116 nearline SAS drives over here. We switch on SFX, and the second time we run the benchmark, after the cache is warmed, we see a 10-fold increase. Method 3 is quite similar, but now we're not working at the block level on the controller, we're working at the Lustre file system level, and it's slightly more sophisticated. So here what we do is we buy, again, could be a small number of SSDs, and we give them to the OSSs to use as a level 2 read cache. The clever thing here is that we're using a slightly more intelligent method of selecting which candidates of files to move to that SSD tier. File heat is developed by DDN. It's more sophisticated than an LRU algorithm. What we do is monitor all Lustre objects over time, and we give them new heat values based on the I/O that's been what's hitting those Lustre objects, read or write, and the size of those I/Os. We can define the memory of the system, so we can forget about what happened last week and concentrate on the activity of the data in the past 7 days, or whatever you like to do. So you can tune those arguments via these settings up here. And we get a similar increase. So again, it's about a 10-fold performance increase for 4K random reads. But the point is here that we're slightly more intelligently able to select which of those Lustre objects to move into this tier. And finally, in the last 3 minutes or so, we have IME. So if you're not familiar with IME, it's a much more sophisticated system. It integrates a totally new tier in between the compute nodes and the Lustre file system. It works by running an IME client on these compute nodes, implementing a number of servers on the network which have NVMe SSDs inside them. And we intercept all data issuing from the applications, and we send it, instead of going to the parallel file system, it goes straight to our IME system. And here's a little bit more detail about how it works. There's many points I can try and pull out, but the one I'd like to make clear is within IME, within the namespace of Lustre, we treat each fragment as it's issued from the application as a fragment. So that means there's very few operations that take place when an application issues some I/O to when we make it safe on this SSD tier. The other important thing is you can see a second stage lower in the diagram. So we take these fragments from the application. The IME client sends it to the servers where it's placed securely on a set of SSDs. So that obviously accelerates the application I/O. The second part is when we flush this I/O back to the parallel file system, we try our best to take the fragments of I/O and coalesce them into sequentially aligned parallel file system stripe before sending it to the parallel file system. So that means that Lustre, regardless of what the application is doing, will tend to see many, many more sequential I/Os than would otherwise have been the case. You can read the slide later. We also protect the data by applying erasure coding to it at the client level, so that if an SSD dies or a node dies, we can still access the data and rebuild it. And there's many RAID options we have. So what about performance of that system? So we're lucky enough to have 10 systems also in a rack. And this one's fairly remarkable, I think. So we're currently exceeding, in fact, we're hitting 560 gigabytes a second for reads and very close to that for writes. And we also get 50 million 4K random write IOPS, which is fairly remarkable. And there's no time to go into why and how. We can do that at our booth or later on. But these are measured benchmarks quite recently from the past few weeks. So That's my summary. So SSDs today can be seamlessly introduced into a Lustre file system. With a modest investment in SSDs, we can have some intelligent, policy-driven data movement to maximize the relevant data that goes to those SSDs. We can do that at the block level and the Lustre level. Rather more radically, IME is a ground-up software system designed to implement a distributed cache between your application and a parallel file system. Not only does it accelerate reads, but really accelerates writes, if not to a greater degree. We also have optimizations above and beyond what you'd expect for an SSD, so at the software level, to accelerate small random IOs. We also have optimizations to cater for shared file accesses. So when you've got many threads and a small number of files, that can be a problem for a conventional file system, even Lustre, and we bypass that with IME. We also are in control of how we place the data on top of our SSDs. That allows us to do it nicely. That means we can minimize the write amplification that is seen on SSDs. That means if you put the SSDs in IME, they will last longer than if you put them directly on the parallel file system. And finally, so we're accelerating the application, we're protecting the SSDs, but before that I/O is flushed down to the back-end parallel file system, we clean it up. If it originated as being random small IOs, we will clean it up and send nice sequential parallel IOs back to the Lustre file system. Thank you.
Thoughts, questions, comments? Oh. Going a little slower, I'm sorry. Shadow?
Did you correct understand IME work very nice only with data may be divided into equal parts between clients? Or it will be have a different block size between clients or?
You're referring to the IME?
Yes, I see you use a distributed hash table to address blocks. So it means each blocks should be addressed via this table, so the data should be aligned to these blocks. So yes, and don't have a cache coherency between clients.
That's half correct. So what we do is for every fragment that's issued from the application, we take those into a client buffer, and in that buffer there's headers, which include the inode offset length of the fragments contained in that buffer. Those inodes offset lengths really correspond to the data that we can input into this DHT to locate our data later on. We implement closed to open file consistency, so once the file is closed, then the whole system is entirely consistent, similar to NFS version 3.
James, thanks.
Thank you.